Have you ever wondered how electricity gets to your house and powers your devices without killing you? Say hello to the transformer. Here's what it looks like. It looks boring, and to be honest, it really is. It's an iron core and two f***ing wires. It's used to step up or step down voltages. Let's talk about how it works.
A transformer can be modeled with several complex formulas such that it takes an applied alternating current, uses the properties of Ampere's law to induce a time-changing magnetic field, but really it's actually pretty simple. As an alternating current goes through a coil of wire, it does something called induction. This operates by something known as Ampere's law.
Ampere's law states that a current flowing through a wire creates a magnetic field.
So now you've got an induced magnetic field, but what does this iron core in the center do? Iron is much more conductive than air, so it allows the magnetic field to more easily travel through the transformer. If, hypothetically, a donut was more conductive, you'd use a donut. But it's not. It doesn't work, trust me, I've tried. So we use an iron core, and a magnetic field travels through it, and as this happens, the magnetic field affects the second wire coil, inducing a voltage in it due to the Faraday Lenz law.
The Faraday Lenz law states that voltage induced as a result of magnetic fields is proportional to the rate of change of the magnetic flux. But what is flux?
Think of flux as the amount of water passing through a fishing net held in the middle of a river. The larger the loop, the more water that flows through it in a given amount of time. If you've got a faster river, the same thing happens.
Okay, so now that we've got flux defined, let's move forward. Recall that this flux has to be changing over time in order to actually generate a voltage. However, if the current and thus the magnetic field is constant, the rate of change of flux is zero and no voltage is induced. Thus, it is important and vital that a time-varying current is used. Okay, so this explains how voltage ends up on the other side, but how does it change the amount of voltage to make it more suitable for everyday devices?
If you look at this diagram of a transformer, you'll notice that one side has more coils of wire. This is because there's a simple relationship between the amount of voltage on each side of a transformer and the number of coils each side has.
So what would you do if you wanted a step-up transformer? What would you do?
Simple. You just increase the number of coils on the output side.
Oh yeah? What about a step down?
Simple. Just do the opposite.
Great, we've got that covered. But what are some examples of everyday transformers? The phone you're looking at right now, instead of paying attention to this video? Guess how it's charged? Your charger contains a 24-to-1 step-down transformer that lowers the 120 volts from your home's electrical sockets and transforms it to the 5 volts your phone needs. And that electricity that gets to your house from the power plant, it averages about 50,400 volts. What do you think? What ratio of turns would it take to get down to 120 volts? If you want to check your calculations, click here to subscribe, and next week we'll upload a new video and walk you through the math.
See you next time!
It's the amps that kill you though.